In this third video from chapter 8, integration techniques, we're going to learn how to solve integrals with trigonometric substitutions. This will involve three types of integrals that look like what's below. So in the first type, you notice that we have a squared minus x squared. If a is a constant and x is a variable, we're subtracting the variable squared. In the second type, we're adding the constant squared and the variable squared. And in the third type, we're subtracting the constant squared from the variable squared, and all of these are under a radical. Well, we can't do integrals of this type that involve the variable squared under a radical. Can't use substitution technique because that would require that we have an x in the numerator, x to the first power. And so there turns out to be an interesting alternate method for solving integrals of this type that will involve trigonometric substitutions. So let's go to the next blackboard to see how this is done. So we start with the Pythagorean identity. We solve it for cosine squared. We multiply everything through by a squared. Here I've changed the input variable to theta, which is important to do so that our substitution works out. Now we're going to let x equal a sine theta, and let's see how that changes our equation. So that makes the right hand side a squared minus x squared. It leaves the left side unchanged. And now let's take the square root of both sides of this equation, where we see that the what was in the radical comes out with the substitution as a cosine theta. So this is the substitution, this right here, that we use when we have a radical of the type a squared minus x squared. And then the radical comes out as a cosine theta. Okay, let's see what we do when we have an a squared plus x squared type of integral. So we start with the Pythagorean identity. We multiply through by a squared. First we divide through by cosine squared, and divide everything through by cosine squared theta, and then we multiply everything through by a squared, and we arrive here. Then we let x equal a tangent theta in this case. That changes the equation into this. And then we take the square root of both sides and arrive here. So the radical turns into a secant theta, and the point is that when we have a radical of this type, we're going to let x equal a tan theta to get the expression a squared minus x squared out of the radical. So the radical turns into a secant theta. And then the final type is when we have a radical of the form x squared minus a squared. Since we've gone through this twice before, I'm not going to go through it in all of the detail. It's very similar. We're going to let x equal a secant theta, and then the radical turns into a tangent theta. So let's summarize all of the substitutions that we do when we encounter integrals of these three types, which is found on page 172 of your text. So in this first type, we let x equal a sine theta, and then the radical a squared minus x squared turns into a cosine theta. We should also note that our dx is a cosine theta, d theta. So in the second type, we're going to let x equal a tangent theta. The radical a squared plus x squared turns into a secant theta. The radical a squared plus x squared is a secant theta. and the dx is a secant squared theta d theta. And then in this last type, we let x equal a secant theta. The radical x squared minus a squared turns into a tangent theta, and the dx is a secant theta tangent theta d theta. So let's take a look at an example involving each one of these substitutions. These examples 1, 2, and 3 are found on page 173 of your textbook. So example 1 is an example of this first type right here, and so that means we let x equal a sine theta. The a in this case is 2. So we're going to let x equal 2 sine theta, and the dx, or the radical, turns into a cosine theta. So that would be 2 cosine theta in this case. So square root of 4 minus x squared turns into 2 cosine theta, and the dx becomes 2 cosine theta d theta. So we're going to move everything in the integral over to the variable theta. The numerator is, as we just noted, 2 cosine theta d theta. The denominator turned into 2 cosine theta, and so we've got a lot of cancellation happening, and we're just left with the integral of d theta, which is theta plus c, and theta is what? Well, if we look at our substitution, x was 2 sine theta. So that means that sine theta equals x over 2, or theta equals sine inverse of x over 2. And so that is our result, sine inverse of x over 2 plus c. And that should look, that result should look familiar. This is something that we derived in chapter 7 by differentiating the sine inverse functions. So here's another way to arrive at the same integral form. Okay, let's move to example 2, where we have an integral of the a squared plus x squared type, or integral of the square root of a squared plus x squared. So here we have an a squared plus x squared. It's not under the radical, but that doesn't matter. So this is a type 2. X is going to be a tangent theta. A is 3, because 3 squared is 9. A squared plus x squared is going to turn into 9 plus x squared isn't going to turn into 3 tangent theta. It's going to turn into, or not 3, right? In the example case, we got a secant theta, but there's no square root sign, so it's going to be 9 secant squared theta. And the dx is just the derivative of tangent, which is going to give us secant squared with a constant of 3 out front. So the dx is 3 secant squared theta d theta. The denominator we just said was 9 secant squared theta. And so that the secant squareds cancel out, and we've got 1/3 d theta, 1/3 theta plus c, and as before, the theta is the inverse trig function, In this case, it is 1/3 tangent inverse of x over 3 plus c, and we can see that that's coming from solving this equation right here for theta. This is an integral form that we also derived by taking the derivative of inverse trig functions, the tangent inverse, back in Chapter 7. So let's move to the third example. This is an example of this third type. The a in this case is the square root of 3, so the radical, so the substitution is square root of 3 secant theta, and the radical is going to turn into 3 tangent theta. And the dx is square root of 3 secant theta tangent theta d theta. So what does the integral turn into? Well, the numerator is square root of 3 secant theta tangent theta d theta, and the denominator is square root of 3 tangent theta, and so the tangent thetas cancel. And we don't have such an easy integral this time. We're left with the integral of secant theta d theta. To do this integral, we need to do a little trick, which is to multiply the numerator and denominator by something so that it turns out to be in the ln form. Let's go to the next blackboard to do that. So the integral of secant theta, we're going to multiply the numerator and denominator by secant theta plus tangent theta. The reason for that is that because that gives us secant squared theta plus secant. So if we let u equal secant theta plus tangent theta, which is this denominator right here, we see that when we differentiate secant theta, we get secant theta tangent theta, and when we differentiate tangent theta, we get secant squared theta. And so the denominator is u, u, and the numerator is du, and so we get ln of u. But u is secant theta plus tangent theta, so we get ln of secant theta plus tangent theta plus c. So going back to where we were, this is ln of secant theta plus tangent theta. Now, to finish this problem, we have to set up a triangle relationship like we did in Chapter 7 when we were working with inverse trig functions, because we actually are working with inverse trig functions. So let's set up the triangle that comes from this substitution that we did. So if we go back to this substitution right here, x equals 3 secant theta, that's the same as theta equals secant inverse of square root of x over 3. Or, I'm sorry, of x over square root of 3. And the secant is the hypotenuse divided by the adjacent. And so the hypotenuse is x, and the adjacent is the square root of 3, and by the Pythagorean identity, this side of the triangle is x squared minus 3. When we do these types of problems in section 8.4 and set up the triangle, it turns out that one of the sides of the triangle is always needs to be that radical in the integral. So if we go back to where we left off, ln of secant theta plus tangent theta, then what are we going to get? Ln of secant theta. Well, what is secant theta? Secant theta is h over a, and so the hypotenuse is x, and the adjacent is square root of 3, and then tangent theta is opposite over adjacent. Here is the opposite side of the triangle, and here is the adjacent side of the triangle, and then we're done with this. In the textbook, you see for this problem that we've gone through a check on page 174 to verify that this answer is correct. So let's do one final problem of this type that is of this first case here, but it's going to involve going back to the form that we did in the previous section. So this is a squared minus x squared type, which means we let x equal a sine theta. The a is 4, so x equals 4 sine theta. The radical turns into 4 cosine theta, and the dx is 4 cosine theta d theta. So that takes care of the dx and of the denominator, but we've also got this x squared from the numerator, so x squared would be 4 sine squared theta. And so we do have cancellation as before, but we're left with the integral of 4 sine squared theta. That should be a 16 here. When we square 4 sine theta, we get 16 sine squared theta. So let's pick up this integral. 16 times the integral of sine squared theta here on the next blackboard. We use the identity that applies when we have an even power of a trig function, which is 1 minus cosine 2 theta divided by 2. I'm going to put the over 2 out front of the integral, and so we're integrating. We can complete the integration, and so we've got 8. The integral of the 1 is theta. The integral of the cosine theta is sine 2 theta over 2, and so that gives us 8 theta minus 4 sine 2 theta plus c, and now we have to go back to our triangle and our previous substitutions to see what we have. Well, our substitution was to let x equal 4 cosine theta, so x equaled 4 sine theta, so theta was sine inverse of x over 4, and we also have a triangle, and in that triangle x over 4 equals sine theta, and sine of theta is the opposite over the hypotenuse, and so this side of the triangle is x, and this side of the triangle is 4, and the base is square root of x squared minus 4. Remember we said that that base is by the Pythagorean theorem square root of 16 minus x squared. Remember we said that one side of the triangle needs to be the radical that appears in the original problem. So, do we have everything that we need? Not quite. Let's see here. We've got 8 theta minus 4 sine of 2 theta plus c. We've got this triangle, but the triangle doesn't help us with sine 2 theta. We have to use an identity that sine 2 theta equals 2 sine theta cosine theta. And so then we can write this or rewrite this as 8 theta minus 8 sine theta cosine theta plus c. The theta we said was sine inverse of x over 4, and then from the triangle, sine theta is opposite over hypotenuse, which is x over 4, and the cosine theta is the adjacent over the hypotenuse, which is square root of 16 minus x squared over 4. So let's make note here that sine times cosine is opposite over hypotenuse times adjacent over hypotenuse, and when we multiply all of this out, we get 8 sine inverse of x over 4 minus x times the square root of 16 minus x squared divided by 2 plus c. So this one is fairly complex to do. It's not anywhere near as straightforward as examples 1 and 2, which were just inverse sine and inverse tangent. So with this fourth example, we have completed this video on trig substitutions. Go back once more to the substitution main page. A squared, this is something that you would want to bring on a sheet to your test. How to set up these problems when you have the square root of a squared minus x squared. Here's what x equals, here's what the radical turns into, and here's what dx is. When you have a square root of a squared plus x squared, or you don't even need to have a square root, here's x, here's the radical, here's the dx, and when you have square root of x squared minus a squared, here's the x, here's what the radical turns into, and here's the dx. So we'll do more examples of these types of problems in class. This concludes this video on section 8.4 in the text.